उड़ गया। अब देखो। आ रहा है? प्रॉपर। ठीक है, बंद कर दो नीतीश भाई ऐसा। हाँ हाँ अभी। हेलो, चेक। हेलो। हेलो। है ना, कोई इशू? ठीक। और वो टाइम से ही करना पड़ेगा, टाइम से पहले नहीं। उस तभी वो ऑपरेट होगी। वो पहले कर दिया था इसलिए नहीं हो रही। गुड मॉर्निंग सर।
How's that تمام؟ GNN. कल कल वो देख रहा था, साउंड थोड़ा कम है।
B transpose because of B from lines. And now GNN model is defined using this GNN dynamics we will use always. Or it can be written in form. A transpose, E of T, B transpose. This model we will call GNN of ABD. If we consider the error function defined as D minus AVB, here we have gamma, but it does not mean that we use gamma in GNN design. We used minus gamma. Okay. It works. Mhm. Okay, okay. It is for tutorial. Mhm. Okay. Mhm. Mhm. Here. One very interesting result, and very important, given in main theorem, main theoretical result about convergence of defined GNN of ABD model. Must remove something. We want to solve equation AXB equals D. Yesterday we spoke about possibility to solve this matrix equation. We spoke about consistent, non-inconsistent case. This matrix equation is consistent if and only if this condition is satisfied. A dagger D, B dagger D equals D. Dagger here means Moore-Penrose inverse. Important is to mention that instead of Moore-Penrose inverse, here can be arbitrary one inverse. Theory allows here arbitrary inner inverse, arbitrary one inverse. And general solution is given in the form enter A, right? Time is arbitrary. Arbitrary, of course, of appropriate dimensions. This set with arbitrary y represents least square solutions. There are least square solutions with arbitrary matrix. And if we choose only first part A dagger, B dagger, it will be less approximate solution of minimal norm. It is best approximate solution or more pendulous solution. This theoretical result, this theorem 1, from this paper says that convergence obtained, result of convergence obtained by GNN model is obtained replacing arbitrary matrix by initial state. It's a very important result. So if we change initial state, we will obtain different solutions, different least square solutions. And using all possibilities to change initial state, we will change the least square solutions. When we use zero initial state, here and here, what will happen? Zero initial state, we will have now this, we will obtain more pendulous solution, we will obtain best approximate solution. So best approximate solution is obtained in one moment, with one choice. In the afternoon, we will try with the different choices of initial state and compare obtained result with our. 10 minutes, waiting 10 minutes more.
Yeah.
Okay. Here is discussion about the importance of obtained result in theorem 1. Here is discussion about set of least square solutions. Theoretical solutions. These solutions are given according to theoretical result, but according to results obtained in the theorem, GNN model will give a result derived replacing arbitrary matrix by initial state matrix. If of the same in a discrete time case, when we try to minimize the matrix norms in discrete time and use classical gradient descent method, the result was the same. Initial state is very important in defining the result. If we start from one initial point, we will obtain one result. If we start from another initial matrix, we will obtain another result. All these results are least square solutions. Only one is unique, and it is solution of minimum norm. Important is to mention that this condition must be satisfied, but it is not problem with GNN model. It is problem with theory. But the GNN model even if this condition is not satisfied, will give one result. It is another priority of continuous time models. Theory has no solution if this condition is not satisfied. GNN model will give a solution. Okay, here we can see this possibility. We have enough time. Model which we consider is linear GNN of ABD, which means here we use only minus gamma. Here should be minus gamma. It is general model. Another possibility to improve behavior of GNN model is to put here nonlinear activation function. Denoted here as a calligraphic F. So nonlinear GNN model is given in the form and derivative of things is equal to minus gamma calligraphic F gradient of error function of goal function. Calligraphic F is defined using one appropriate activation function, small f, this notation means matrix. Here is matrix with elements Aij, and here is matrix with application of nonlinear activation function. General rule is that activation function must be odd and monotonically increasing function. Each odd and monotonically increasing function can be used for nonlinear activation. Most popular activation functions are, of course, linear activation function. It is practically not an activation function, but theoretically we can consider bipolar sigmoid activation function, power sigmoid activation function, basic activation functions. Well known in literature, first activation functions and very popular in machine learning and in artificial neural networks. Here are two finite time convergence activation functions. If activation function is appropriate, then such a GNN model can achieve finite time convergence. Theoretically, we can find the time in which convergence will finish. There are two selected finite time activation functions. First one, and still popular, is Lie activation function, or sine bipolar bipower function, defined in this way. Here R is parameter between 1 and 0, 0 and 1. What is interesting here? And it is typical situation for finite time activation functions. Here we have one small exponent because R is between 0 and 1, small exponent, and one big exponent. If we use only one exponent, then error function disappears during time, goes to 0, and this term goes to 0. And gamma must be bigger and bigger to neutralize this, how to say, this zeroing. Here we have another term. This term first, it's small exponent. And when x is small, then this term will be bigger. And always we have fast convergence, and gamma should not be as large as possible. Here are graphs of main nonlinear activation functions. You can see typical rule, all odd and monotonically increasing. All activation functions have these properties. They are odd, symmetric with respect to 0, 0, beginning of coordinate system. Here is linear. Of course, we can imagine more and more nonlinear activation functions. Always this property must be satisfied. Here is a new trend. It was enough use two powers, one small, one big. Sign tunable function here, use one scalar factor, and then many researchers put with more terms, even with more terms. Sometimes put here exponential function. Of course, it is good to put here exponential function and force the convergence, reduce gamma, and from that here it will be exponential function. Okay, it's time to stop.
Okay, thank you very much. If you have any question, please.
How we can identify which estimation function is best for our system? How we can identify which estimation function is best for our system?
All activation functions are good and improve convergence. As the nonlinear if we apply activation function, we will obtain faster convergence. If this activation function is based on odd and monotonically increased function. Finally, finite time convergence model activation functions will be closed. These activation functions enable finite time convergence. It is important in robotics, we must obtain convergence in some defined time. Some activation functions are tunable, so we can define parameters so that we can obtain convergence in wanted time, in defined time interval. Desirable is improve convergence, obtain finite time convergence. Which is best. Always can find better. Always. I will put here an exponential term. Here, for example, I will obtain better. Another one will say, I will put here gamma of t, variable gamma, and this gamma will increase and will be better. Goal is to increase term which is before gradient of goal function. No best. The final answer is no best. Always then we found that I will use Ackermann function here, which grows very, very big.
So using any odd function,
Right.
so using any odd function is guaranteed to be converged, or is there some heuristic to use a function as a
Nonlinear activation function. So, yes, yes, in general, many.
It may be sometimes it may not
Odd
converge.
and monotonically increasing. And we devise new odd and monotonically increasing function, it can be new activation function. Which will be new. General rule for finite time convergence activation functions is to use one small power, small exponent, and plus one big exponent. Such form leads to finite convergence. This one is odd and monotonically increasing, but convergence is in infinite time. Theoretically, we go to the exact solution. No, nothing. Never will obtain. We'll stop working with some defined time interval and obtain some approximation. Only to purpose.
So is there any other question? If no, let's be. Down for it. Six. It's six. This.
It is basically not algebra is here.
Yeah.
Here it has, here it has this. Sometimes if I cannot follow it's
Okay.
Shall we start? Okay.
so really right.
Okay. So This is a continuation of our last class. We discussed about, in our last class, we discussed on the sensitivity analysis of any decompositions. Also, we discussed some basic things, is not it? And we have seen the using elementary operations, how we can perform Gaussian elimination and dualistic factorization. Also, we have seen how to solve by using backward and the forward substitution. Also, we have seen that how many flops we require by performing backward and the forward substitution. Okay. At the same time, we have seen the LE decompositions. If you perform, then it will take 2 n cube by 3 blocks. Okay. So entire problem to solve Ax equal to B, you require 2 n cube by 3 blocks. That means order of n cube blocks. And this decomposition, so whatever LE decomposition, this is particularly important when the matrix is ill condition. So when matrix is ill conditioned, in that case, LU has some problem. That we can see in our next example. Not working.
Yes, I had this situation several times. They should show us how to solve problem.
Just click on.
Just click on screen.
Okay. Yes, good. So now here you see, I'll give you different examples for well condition as well as for ill condition. So how you'll perform, say for example, you have a well conditioned system. Consider this matrix A equal to 2, 1, 1, 3 and B equal to 3, 4. Okay. And then you just perform the LU decomposition and you'll be looking, this is L and this is U, and where L is a unit lower triangular because diagonals are 1, 1. Okay. And now you solve this equation, you see the solving the system Ax equal to B in 2 steps. So first you are solving Ly equal to B by using your forward substitution. And so once you do this, and you will get y1 equal to 3 and y2 equal to 2.5. Okay. And after finding this y1 and y2, you just do substitute here this y and you can get the x, ux, and here x2 you will get 1 and x1 you will get 1. This is the exact solution is 1, 1. And now you do small changes in this, the part B part. The P just you are changing 3.01. Instead of 3, you are changing a little 0.01. You know, one of the empty you are changing. Now you do solve the same equation. Now here, if you do solve Ly equal to B with this B dash, okay, and then you will be getting y1 equal to 3.0 and y2 equal to 2.49. Okay, and similarly, you just solve ux equal to y with this. You will get x2 equal to 0.998 and this 1.0206. So from here you see the changes 1, 1 and it is 0.998 and 1.006. That's why this is well conditioned because here we have changes 0.01 and the solution is getting changing relatively. Okay, that's why this system is called well conditioned. Understood? So if you are allowing a small changes here, and then your solution would get changed small. Okay. And now the next example you see. The solution changes only slightly in the before. Therefore, this system is not sensitive to small perturbation. The condition number A is small. Okay. So whatever we did previous example, this is not sensitive. And if you do a small change, and your solution will get small change. Okay, that is well conditioned. It means. Now you take another example. Here is the ill condition. And now this matrix is 1, 1, 1 and 1.001. And B is this 2.2. Now again you perform the LU decomposition for this matrix. Okay. So once you do this A equal to LU, now you have this LU, LG unit lower triangular and it is upper triangular matrix. Now same way we do solve with this equation, with this P, and we'll get the Ly equal to B and Y1 equal to 2 you will get, and Y2 you will get this. And you do substitute this in Ux equal to Y, and because Y is known, and then you get the X2 equal to 1 and X1 is 1. Okay. So this is the solution, 1 solution is there. Now you are changing again the B part, that is B dash, you are changing the second component to 0.00002. Okay. And the Y2 you will be getting this one. Okay. And then corresponding X2 would be 2 and X1 equal to 0. So now you can think about this. What was the X1, X2, this 1, and this X1 is 1. Instead of that, you will be getting X2 equal to 2 and X1 equal to 2. So as compared to the relative change here, and this is the great change, it's a large change. Okay. The small change, you are giving 0.00002, and the solution is getting here is 1, and here is 2. Here is 1, it is 2, and this is 1, it is 0. So this system is called infinite. That means if you are changing it slight, small, and the solution is getting large. So this means this matrix, whatever we have given in our previous slide, is infinite. And this matrix is very sensitive. That means if you do small change, and it will get large change in the solution. Now here you see, so for that kind of problem, you are doing what this is a matrix here. Sometimes you are doing partial pivoting. Okay. So if it is an ill condition, then you do partial pivoting. Okay. Say for example, here is 0, 1, 1, 0, and B is 1, 2. Here LU decomposition without pivoting helps because the pivot element is A1, 1 here. Okay. The leading to division by 0. So we must use the partial pivot. This is the position where you should use the partial pivot. Otherwise, the pivots won't get, you will be problem here. Okay. So then you are using the permutation matrix. Okay. And you just use a good row and column you can change. Okay. Now LU decomposition is straightforward and the system can be solved stable. Now what do we see here? The condition number. This is, in last class you have seen that condition number. What do you mean by condition number? I'll discuss again what is the condition number and more details and its properties. And it measures the sensitivity of the solution to the perturbation in A or B. It measures sensitivity, how much your problem is sensitive. It is well conditioned or it is ill conditioned. So LU without pivoting may be numerically unstable, as we have seen. And also you have seen a couple of examples in your last class, yesterday's class. And LU with pivoting more robust to round off and the instability. Okay. And the perturbation input may cause large error if A is ill conditioned. Okay. Now we will read some details on matrix norm. Okay, there are a lot of norms already you are using, and in your yesterday's class also you have seen a lot of norms, 1 norm, 2 norm, infinity norm, Frobenius norm. All details we will see here. So what do you mean by matrix norm? This matrix norm is a function that assigns a positive scalar to a matrix and satisfies certain properties similar to the vector norms. Matrix norms are widely used in numerical analysis, optimization, and linear algebra. Basically, as you know that from the Euclidean norm, in the case of vector, and is a function from Rn to R plus, and you have certain properties of the norm, and that is Euclidean norm. Similarly, you have the matrix norm. Okay. So basically, we are using this norm when you need for the optimization. Say, for example, you want to find the least square solution. If you don't have exact solution, in that case, you need least square solution. So you have to.
Basically used in gradient neural networks.
Yeah, everywhere we are using because this is GNN also. Yeah, we are using everywhere. Because whenever system is a non-square and it is singular and you don't have exact solution, in during that time you are using the matrix norm to get the solution. Okay. Now here is the function from this Rm plus n to R plus. Here R plus you can write. This is a matrix norm and it satisfies the following properties. This is non-negative if it is greater than equal to 0 and if and only if a equal to 0. Okay. If it is 0 then 0. Then scalar multiplication is alpha of a norm. This is equal to this for any scalar alpha and this is called triangle. All these conditions will be satisfied in case of vector norm. But the extra one we need, this is called submultiplicative norm. This submultiplicative norm is the, this one is the matrix is this AB, the product of AB norm. This is less than equal to norm of A. And this is one extra property, this is matrix norm you are getting, which one is not. In general, you find in the matrix, this is matrix submultiplicative norm. These properties make the matrix norm analogous to vector norm, but applied to the matrices. Okay, this is exactly same what we did. The several matrix norms are commonly used to practice, having different properties and interpretation. The most frequently used matrix norm are the following. These are the norm. This is the Frobenius norm, and you have seen many use of this Frobenius norm in our last class. Okay, and this Frobenius norm sometimes it is called Euclidean norm. And if all the matrix, if you keep in the vector form, and you just add, you just take the absolute value and square, and take all the summation and square root. This is I varies from 1 to m and j varies from 1 to n. If the matrix is of size m by n. Okay. And this norm is equivalent to Euclidean norm of the matrix when viewed as a vector. As I told you, the Frobenius norm has the following properties. This is invariant under orthogonal transformation. This is very important property where we are using in case of least square problem for solving least square problem. Say, for example, you want to solve this A, you start. If you take this is taken, okay. And if you are taking the norm of this and norm of this, it is exactly equal to norm of this. And where u is, u in there, unitary. Unitary. Okay. So many cases you are using this transformations because when solving the matrix equation in iterative process, what you do, you transform that matrix into the sparse vectors. Say, for example, if you have a matrix, complex matrix, you can transfer to the triangular form. That is called Schur's decompositions. So any complex matrix, you can transfer into T equal to U star A. Any complex matrix, where T is the upper diagonal matrix. So in this kind of problem, if you take the norm of this, and that would be this you get. So if you have the million by million matrix and millions of entries are there, you can make it half in the first part. So this is the beauty of this Frobenius norm. This is unitarily invariant. That means it won't affect if you multiply either unitary matrix or orthogonal matrix. If it is a real matrix, then you have also similar kind of triangularization with orthogonal triangularization. Say, for example, here is your complex matrix, and when here is real matrix, say n plus n, then also you can write A T equal to that this is not as exactly like the previous case, here T is quasi of a triangle. T is quasi of a triangular. This L these diagonals can be 1 by 1 or 2 by 1. Okay. So this is also called another form of Schur's decomposition. If you have matrix which is a real matrix, also you can write in the quasi-triangular form, where you will get a lot of sparse matrix. And you can take the norm both sides, and the original matrix norm and the triangular matrix norm would be exactly same. So this is much helpful when you do optimization, because you can save a lot of time. Okay. So similarly, you have the another property. This is submultiplicative norm. It will be satisfied, and you can see this satisfy all the three properties as we have discussed in our previous slides. Okay, and this is called a matrix norm. And similarly, you have commonly used in optimization, as I told you, approximation problem, and another norm we are using, that is called operator norm. That is, an operator norm is a matrix norm based on the action of a matrix on a vector. Okay. So this is, it is familiar, and this is norm of P, this supremum of x not equal to 0, x norm P and norm of xp, P equal to 1 to infinity. Generally, we are using P equal to 1 to infinity. You can take P anything 1 to infinity, but in application point of view, we use only 1, 2, and infinity. Okay. So here, if you put P equal to 2, you will get the two norm matrix. Okay, two norm of matrix, and also you can use the maximum, because this is a compact set, and the maximum will exist, and yes, it is coming from the functional analysis when you play from T the operator from Banach space or non-linear space to non-linear space. Sup norm you are getting that. From there it is coming. This is called matrix norm, because this we are playing the matrix. Okay. In case of finite dimensional case, matrix and operator, they behave same. And here also, in case of two norm, also it is unitarily invariant. In case of two norm, you have this T equal to U star, then you have this two norm. This is the beauty of this two norm of matrix. This is unitarily invariant. If you do multiply 1000 unitary matrix, it won't affect your solution. And a least square solution. That is important part of this. And this, for calculating this two norm, you can use singular value decomposition that we'll discuss later part of this session. This maybe. Now, as we have discussed, this is one norm. The one norm of matrix is just you are taking the column sum. Okay, you just take this and the maximum of J. You take the maximum one. Okay, and this is the maximum absolute value, this column sum of matrix. Similarly, in this infinity norm, that is maximum row sum, that you take the row sum and take the absolute value and take the maximum one. That is called infinity norm of matrix. This is the maximum absolute row sum of the matrix. As I told you that the spectral norm, whatever we have shown you, the operator norm, that can be calculated from the singular value decomposition. So later part we will discuss the any matrix, again complex matrix, either it is a square or it is a non-square matrix, can be transformed into A equal to U star, sigma, and B. Okay, this sigma, say for example, the rank of this matrix is rank of A matrix is say R, and A is say M by N, C M by N matrix, and this is the size is N by M, and this is M by N, and this is N by N, and U and V are unitary matrix. Okay, and this sigma contains this sigma 1, sigma 2 up to sigma R, and the rest are 0, and it mentions the size of this matrix here, called the sigma n, and it mentions like this, sigma 2 greater than equal to sigma r, and this sigma r is strictly greater than, because this should be non-zero. Okay. Since the rank of this matrix is R, you will go up to R. Okay, and the rest of the entries will be 0. And you see the beauty of this 2 knot. If you use this 2 knot, either Frobenius knot or you take 2 knot. For the Frobenius knot, you just take the summation out. Sigma I square, and this is square. I will from 1 to I. Yes, this is Frobenius knot. And if you go for the 2 knot is equal to, this is equal to sigma 1, which is equal to sigma max A. What I mentioned here. This is maximum singular value of this matrix A. Okay. Now here you can see that this is one example. This is infinity norm also we have this maximum from Aij, where this condition will satisfy. The matrix are multiplicative. This A, B, norm less than equal to norm of A and norm of B. This condition won't satisfy for this, but all other cases it would satisfy. So this is one example where you can say that the matrix submultiplicative norm won't satisfy. Okay, this norm gives maximum entry in the matrix and is often used quick estimates of matrix magnitude, because many people are using this norm as well. Okay, and this is easy. That's why many people follow if the other norms makes difficult. Now we are talking about this condition, as you have seen already many times, the condition number. This condition number, if a matrix is non-singular, then you can define the condition number like this. Okay, and this norm either you can take 1 norm, 2 norm, or infinity norm. Okay, or you take the Frobenius. For any norm, you can calculate this. And this norm is matrix norm, and inverse is the norm inverse of it. The condition number can be computed with respect to different norm, but the most commonly used norm are 2 norm and 1 norm. Okay, so many applications people use 2 norm. That's why this is commonly used this. The condition number Ka provides insight into how errors perturbation in the input data will affect the output. Okay, as the condition number will increase, okay, then you will be in the danger zone. That means your problem is very sensitive. As you go and increase condition number will increase, your problem will be sensitive. As I have shown examples for LED composition, ill conditioning will increase. That means your solution will be very sensitive. If Ka is large, the matrix is ill conditioned. In this case, small change in A and B lead to large changes in X. Okay, and making the system sensitive to numerical error. And the condition number is always greater than or equal to 1, because this is simplest form. You can write this identity matrix equal to, if A is the non-singular, you can just write this. Okay, and norm of I is equal to, which is norm of A less than or equal to A inverse. Okay, this case is greater than or equal to 1. So condition number always greater than or equal to 1. So when it is 1, if the matrix is unitary matrix and a Hermitian matrix, unitary matrix and orthogonal matrix, in that case, condition number would be 1. So that means that kind of matrix is well conditioned. Okay. And now the question is, suppose a matrix is singular. Can we find this condition number? Yes, we can find the condition. In that case, you just check this. I discussed later part. This A equal to A plus, this pseudo inverse or mode Penrose inverse. And in that case, your condition number can be coming this sigma 1 by the sigma, say R in that case. This is condition number. This is the maximum singular value. This is the minimum singular.
R is the rank of
Yeah.
matrix.
I have already defined this previously. The R is the rank of the matrix. So even if the matrix is singular, you can find the condition number of this matrix, where sigma 1 is the maximum singular value of the matrix and sigma R is the minimum singular value of the matrix, because we have taken the rank of the matrix in the R. Okay. Okay. In practical terms, if the condition number is large, it indicates that system equation is difficult to solve due to numerical instability, and the solution may be unreliable. You cannot take this. Okay. So for linear system Ax equal to B, the condition number provides insight into how errors in A and B will affect the solution X. If the condition number A is large, the system is said to be ill conditioned, and meaning that even a small error in A, okay, even a small error in A or B can lead to large errors in X. Either you one of the entry of the B part or A part, you are changing even as a very small 10 to the power minus 6 or maybe around that, and then your solution may get changed immediately. I'll show you that several examples how it changes. Okay. Now the effect of errors. Say for example, if you are changing the system, that means if you are changing this, say A plus delta A, okay, and this is X cap, and this is B plus delta B. Okay, and the original system is X equal to B, how it relates with the condition number. Solution will get changed this. This is the relative error. Okay, and this is condition number times the relative error with the matrix, and this is with the B bar, B vector. And always it is multiple. If the condition number will increase, and the left hand side will increase, even if this is small, sometimes. Okay, where delta X is the error in the solution, and delta A is the error in the A, and delta B is the error in the right hand side of the B. Norm represents the matrix or vector norm. Okay, this inequality shows that relative error in the solution is proportional to condition number of the matrix A, and large condition number indicates greater sensitivity and to errors. So whatever we discussed, we have here you mentioned that you can get this kind of errors if your matrix is ill conditioned or well conditioned. Now similarly, if you do change, say for example, if you are not changing the B part, also you have the new solution will be affected with this condition number. You see, this is one you have. I think here is okay. So here delta X by norm of X, norm of X, this is X, this is equal, less than or equal to condition number times K and delta B by B. And if you are changing this, say Ax equal to B plus delta B. If you have this, then this is the one you are getting the relation. Okay. So if you are changing a little in the B part, okay, and then you have the relative error, this the condition number times the relative change in the B part. Okay. So if the condition number will increase, also this will increase. So it is the effective, either you change B part or only the A part, or you change both the A and B. In all the cases, the condition number will be involved, and you can decide whether your solution is growing or it is gradually decreasing. Okay. Now here, so when you change this matrix, sometimes when you change this small, it depends also. If your matrix is the change of the, if your matrix is diagonal matrix, and you are changing a slightly changed perturbing this delta A in all the terms you are getting. In this type of changing, you won't get you would be getting the good solution, because here is the diagonal perturbation you are making, and you have the diagonal matrix. Always you have, if you have the diagonal matrix, always you can get the good solution. And if you are changing the slightly to the diagonal entries only, the rest of the entries are 0. So in that case, you won't get the effect of conditioning much. Okay. And if you are changing it slightly, and your solution will get affected slightly, not it will blow or it won't be. Okay. So solution will be affected by the ratio of the perturbation in each diagonal entries. So only it will be affected only that part. Okay. Now the sparse matrix, in this, in the case of sparse matrices where most of the entries in A are 0, perturbation in the non-zero entries can have a more localized impact on the solution. The sensitivity of the solution to this perturbation depends on the structure of the matrix and the sparsity. Say, for example, I have not mentioned here. So if you have sparsity, then you can again decrease the size of the suppose X equal to B. And if you have, say, you have a lot of zeros here, say I am taking this K and this is a B, and this is N minus C, and the size of this matrix is this is N cross N. Okay, say I am taking here dx, D is a lower diagonal matrix. Okay, so instead of going to calculate all the entries, so we need to calculate where non-sparsity is there. Okay, because unnecessary we will be taking a lot of loss. So here, say I have this D11, 0, D2, D21, and this is D22. I am making here this is K, and here again here you have this is size of P, this is N minus K, and this is N. This means KO and K columns, and this is N minus K column, and like this you have. Because by looking this, I have made a partition. Because till the kth part is 0, so I have used this, and this is say this is y, and you take y1 and y2, and also you take this is k, and you are making conformal partition. That means where rows and the columns will be same, where you can do multiplication. So if you do this, dy equal to b, so what you get d11, and this is 0, d21, and d22. And this is y1, y2, and this is equal to, say, this is 0, and this is okay. Okay. And this I can directly multiply. What I get? The d11, y1 equal to 0, and this I get d21, y1 plus d22, y2 equal to dk. Yes, sir? Because G11 is non-singular, because G is a lower triangular matrix and it is a non-singular matrix. If it is non-singular, that means this and this will be non-singular. Why it is? The determinant of G equal to determinant of G1 into determinant of G2. If one of this determinant will be 0, this will be singular, so both these determinants will be non-zero. So this matrix will be non-singular and this will be non-singular. So here we will be getting y1 equal to 0 because determinant of G11 is not equal to 0. Yes? And once you put this, you will get G22, y2 equal to dk. So here you are reducing this problem to this. Okay. And here the size of this matrix is n by n. Here is the size of the matrix is n by n minus k. And for this, you require order of n square. And for this, you require order of n minus k whole square. So drastically, you are changing this clause. Okay. So instead of fitting problem to your computer, You just decide here. So what kind of problems I'll fit to your computer so that you'll save your time. Okay. So this is what we have, the since sparse matrix, we make always a matrix to be sparse. That is the reason why we make always, we'll try to make our matrix to sparse. So in the case of sparse matrix, where most of the entries in A are zero, perturbation in the non-zero entries can have a more localized impact on the solution. The sensitivity of the solution to this perturbation depends on the structure of the matrix and the sparsity. And so it's a structure in the sense, so it is the nature of the structure. Say, for example, your problem is symmetric, okay, and you are changing the perturbation matrix here is also symmetric. Here, some applications they need structure preserving, okay. If it is symmetric, you do the perturbation symmetric, and you get the solution. And sometimes you don't bother about the structure. Whatever matrix you have, just you give the perturbation. So structure preserving depends on the structure matrix and the sparsity pattern of that matrix as well. Okay. The for symmetric matrices, perturbation may result in changes in the eigenvalues and the eigenvectors of the matrix. Okay, the perturbation may result in the changes in the eigenvalues and eigenvectors. So if you do perturb and then eigenvalues and eigenvector also will get change. So again, there is a lot of things to understand about the sensitivity of eigenvalues and the eigenvectors. Okay. And since the solution to a linear system can be expressed in terms of eigenvalues and eigenvector for the symmetric matrices, small perturbation may cause significant shifts in the eigenvalues affecting the solution. Okay. Suppose a matrix is simple matrix. That means eigenvalues are all distinct. And you are doing small changes and it will make it defective. If you defective matrix, you know that algebraic multiplicity and the geometric multiplicity won't be same. It is algebraic strictly greater than geometric multiplicity. And in case of simple, they are same and equal to 1. And also for the semi-simple won't get affected. But when the matrix is very defective, in that case, small change, your eigenvalue will get changed a lot. Okay. Okay. And the conditioning stability of the perturbation. Thus, the stability of the solution to a perturbed system depends on conditioning of the matrix A. If A is ill-conditioned, even a small change, as I told you, this is especially problematic when the solving system linear equation using direct method, Gaussian elimination, or LUT comes, where error may propagate. That we have already seen this. In contrast, well-conditioned matrices are less sensitive to perturbation and the solution remain stable in the presence of small changes. Okay. So sometimes here also perturbing the coefficient matrix in a linear system can have significant effect on the solution, especially if the matrix is ill-conditioned. The relative error in the solution is directly related to the condition number of the matrix, with higher condition number leading to greater sensitivity. That already we have seen. And in error analysis, including the use of the condition number provides a way to quantify the impact of perturbation and assess the stability of the solution. So this condition number also decides whether your problem is stable or not. Now, sometimes you have, when solving linear system, it is important to consider the conditioning of the matrix and the potential for the perturbation, especially in numerical algorithm where round of errors and the other small inaccuracy may accumulate and affect the final solution. So as I told you that there are many kinds of error, human error, machine error, and there are different types of errors are there. So maybe tomorrow we will discuss more on this. So here you see, the condition number will decide whether your matrix is singular or it is non-singular. How far you from your non-singular it is, okay, and singular it is. Say for example, if you have X equal to B and B not equal to 0 and you are changing this, as I discussed previously, that this condition number times it is small and this factor it is coming as I have written in the previous one, that relative change of this error, and this is condition number times this is the relative change of this while a condition number is there. Okay, basically, I want to say this one. Because if you small change here and this condition number will get. K is large, then the small error in B can cause large error in X. Okay. Now here see, as I discuss you that this is system is well conditioned. If it is equal to 1, as I mentioned, this is always greater than or equal to 1. And if it is bigger than 1, and it depends on you whether you allow for that kind of error. And if it is bigger, then it is ill conditioned. And for the norm I equal to 1 and this condition number, this is the small group of this I have mentioned already. And this is inverse independent. If you have the inverse of condition number inverse matrix and is same as the condition number of this matrix and is also scale independent. This is if you scale, if you some scalar, non-zero scalar, and the condition number won't get changed. Because you are taking the inverse of the C equal to 1 by C and both the C will get cancelled. Now here you see the condition number, you just calculate this one and this is A inverse and just take the norm of matrix, okay. And in this case, sometimes one norm and infinity norms are same when the matrix is symmetric. When symmetric, one norm, infinity norm, because row and the columns are same, a row sum and the column sum would be equal. So one norm for infinity norm for the case of Hermitian or maybe for with symmetric matrix, it would be same. As I mentioned here, the condition number Ka is equal to 1. So now here also, this is if a scalar is there and the condition number determinant of this is a to the power n, but here is the scale independent. But in the determinant you have, this is scale dependent. Okay, a to the power n and here is that. The scaling doesn't change the condition. Okay, number one, but it does affect the determinant magnitude. Okay, so small or large determinant doesn't imply ill or one condition. So here determinant is no effect to the condition. So this is some properties of this. Here is one example I can show you that, say for example, if you have matrix this, and again some you can convince that how it affects if you do small change to your matrix when matrix is in condition. So here x is 1, 1, x equal to this, and just you take the part of this 1.01 and the subtract to 0.01, and then you will get this x tilde, you will be getting this one. The very small change in V caused the huge change in x. Okay, huge change in x. Small change in B caused the huge change in x. Why? Because x was in the direction of maximum magnification values. Here, in mass. Okay. In the same manner, it is going towards the singularity. Okay. Now, one example I used to tell that every time the Hilbert matrix. This is very well conditioned. You see, once you see that it looks like well conditioned, but it is not well conditioned. This is positive definite, number one, and the symmetric positive definite. Okay. Generally used to tell if it is symmetric positive definite, the matrix is well conditioned. But this is one example. Sectional that where symmetric and it is positive definite and extremely independent for large n. Okay, and you see as you go and increase the size of this matrix, this says for example Hilbert matrix of size 4 and is 10 to the power 4, and if you go increase H8, it is 10 to the power 10. Okay, as you go and increase the size of the matrix, your condition number will increase. But this matrix is symmetric positive definite. So now here you can compute in your MATLAB. So just you take this, compute the condition number. Say for example, n equal to 3, 6, 9, 12. You just take n equal to 3, 6, 9, 12. Just to put Hilbert n, K1 equal to condition H1, K2 condition 2. And in MATLAB there is a command. If you don't put any 1 and 2, also it will calculate for the 2. Okay, and for the infinity and the Frobenius norm, you can infimum you can put here, but with the inverted comma. So concept A, comma 1, for 1 not. Condition A, if you are not putting anything, that means for 2 not. Condition A, comma, INF with inverted comma for infinity not. Condition A, comma, we just give a follow. It will give you for this now. Okay. You put like this, and you just see all the effect of this matrix, the condition number K1 and K2, and you can put other condition number with respect to other norms as well. So here the effect output is, if you just put this, and you will get this for 3, 6, and 9, and condition number will be like this. And this is with respect to 2 norm, K2, K2, K2 means with respect to 2 norms. Also, you can check for the K1, 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 K infinity, K infinity, K infinity, K Frobenius norm, K Frobenius norm, K Frobenius. Okay. Even though Hn is symmetric, now the conclusion and positive definite, solving Hn x equal to b becomes unreliable for large n. Small changes in b lead to large changes in x. Highlights the importance of using numerical stable algorithm. A matrix can be mathematically well behaved, yet numerically dangerous. Sometimes you might have seen that theoretically everything is fine, okay, but numerically it is not. For example, you have seen the Gram schematic process. It is everything. If it is linearly independent, you will get the orthonormalized vector, and that gives you QR characteristics. But sometimes for the Hilbert matrix, if you can put, that won't give you the result, because you will see the positive definite symmetry, and you will put this Gram schematic process Q transport, that should be identity, it would be far from identity. So this is one, but mathematicians use very frequently the Gram schematic process. So here one result that how you can use this condition number. Say, for example, A is a non-singular matrix. How much you are going to change so that you will be in the domain of non-singularity. Otherwise, you will be beyond non-singularity. This is the condition here. If you do small change, this relative change, if it is satisfying this condition number, then the change this A plus delta A will be non-singular. If A is non-singular, and you give the perturbation with the range of this, and this A plus delta A will be non-singular. Otherwise, it may be singular. The proof is very simple. The linear algebra proof. Say, for example, it is singular. If it is singular, then y non-zero, and you just A plus delta y equal to 0, and you just take this, and y equal to finally invertibility. And you take the norm both sides. And use the submultiplicative norm, this norm of A inverse as delta A. This is 1 less than equal to this one, delta A, and A inverse norm is greater than equal to 1, which means delta A relative change is greater than equal to 1. And this is the contrapositive force, because this is what we got. That means A plus delta A is non-singular. Always. So what I use?
So, after 3 minutes.
3 minutes.
3 minutes more.
3 minutes more.
30 minutes.
Oh, 30 minutes. Okay.
Almost 12, 30 minutes. You have 30 minutes.
I have 30 minutes. Okay. So here you can see this, the condition number Ka. This measures how close A to be singularity. And if delta A, this change of error, this less than equal to 1 by K, then a small perturbation in A preserves non-singularity. Okay. So if you are changing a small, and non-singularity will be preserved. So it doesn't mean that if the matrix is non-singular, that means it is a well-behaved, as we have seen previous example, that it is non-singular, it may not be well made. It may not be well conditioned. Say, for example, Hilbert matrix. Okay, this is symmetric and positive definite, and it is a non-singular, but it behaves drastically in different way as expected. But sometimes we use non-singularity in very often, okay, in our calculation when we would get the infinite state. So in that case, the singularity is again dangerous. Okay, and this spectral norm, this bounds this because minimum of norm of this delta A with the norm of A2, where A plus delta A is singular. This is nothing but the 1 divided by this condition number with respect to 2 norm. And same thing is true for 1 norm and then infinity norm, but just you replace 1 with infinity. Okay. And same thing, whatever we have here, condition number of matrix or the solution, you can also discuss the condition number of eigenvalues. You can discuss the conditioning of eigenvectors also. Right? So, for example, if your matrix, you do small change, right? And you can get the defective matrix of that. Sometimes X equal to lambda X instead of X equal to B, and also same thing you can apply for the case of lambda X. Okay. And simple if A lambda algebraic multiplicity and this geometric multiplicity of all the eigenvalues into 1, then A is called simple. Okay. And if it is simple, this is well behaved. Okay. And you can also make that if the parameter dependent, you can make the differentiation with the matrix. Okay, eigenvalues. And you can also change this this lambda delta plus T plus delta T if it is the parameter dependent. Say for example, if you have the matrix of this form, it is a parameter dependent. The coefficient matrices are parameter dependent. As you have seen, G and N, all the matrices are in the parameter dependent. Okay. We are doing the differential. You have not asked any questions. Why we are making differences? It is possible only when this eigenvalues are simple or semi-simple. If eigenvalues are semi-simple and you can make the differentiation with respect to eigenvalues with respect to T, and it will satisfy all the Taylor series expansion. Okay. If the matrix is not simple or semi-simple, you cannot put the differentiation. Okay. You can make the differentiation for the case of eigenvalue then, and you can do the eigenvalue expansion. So same logic, it is true for here the eigenvalues case, but in the different form. Okay. And also you can discuss about the change in the X also. So if you do change this small in the A, and what is the change in the eigenvectors? And what is the change in the eigenvalues? Okay. So what is the beauty? See, if a differentiation, if you have this Ax equal to xt, and so basically why you need this? You have this x dot t equal to axt. And these are the vector. Okay. Say for example, this is the 1 dot t. And this is x2 dot. This is you need to solve this equation. Okay. So if matrix is simple, then you can easily find your solution. Very well manner. But if the matrix is not simple or semi-simple, then it is not diagonalizable. First of all, it is not diagonalizable. If it is not diagonalizable, you cannot find the solution. You know, in general, you just find e to the power lambda t. Because if A is simple, you can write like this: A equal to S inverse ds. Right. And its solution is coming in the form of e to the power x equal to e to the power this is A xt, x not, say for example, this is x and t, something like that. Then you are putting E A equal to This is equal to S inverse dx. This is S inverse, this is e to the power lambda 1 and k to the power lambda n. And this is yes or no? And this is 0. This. Okay. So once you get the solution, because if it is diagonal, then you can write in the diagonal form and you take the norm, and then you can study whether your different solution is convergent or divergent, and the solution is stable or unstable. So if you are doing in the differentiation, if you are working on the differentiation also, you need this population analysis, and you can check that whether the matrix is simple or defective. If it is defective, then you do small change, you make it into shape. Okay. And sometimes you have seen, suppose if you are working in the machine learning and in the support vector machine. So what generally you do, you have the convex problem. Okay. When you use the KKT, and in that case you need the convexity. And if it is a non-convex, okay, then you cannot use the KKT. Then you have to make it to convex. So that's what you do. You do a small change to that matrix to make it to convex. And then you apply your KKT on the convexity. All these machine learning people are doing support vector machine. People use this condition because sensitivity analysis will come when the problem is not convex. Because then the part is that. Okay, if it convexity is there or the well conditioned method is there, you can apply. The difficulties will come when the problem is sensitive. Understood? If the problem is sensitive, you make it not sensitive. You make it to convex. Then you can handle your machine learning problem. Generally, you use the primary one and then you use the KKT condition. You get documentation. You know. So sensitivity analysis you have to know in every field. Okay, whoever is working differentiation, different the differential equation or pure and applied variability. So convexity will be there. So if it is convex, then it is well conditioned. Then you can make your solution in the easiest way of doing this one. Say as I told you, the change in the solution, and you will get this effect of this. And this is the small proof where you can see this condition numbers effect. Okay. These are the references. You can just see this numerical linear algebra, and you can find in the Google also. And this is the book by Jean Gully, Matrix Computations, and this is David S. Watkins, Fundamentals of Matrix Computations, and also you can see applied numerical linear algebra. This sham and numerical linear algebra for large eigenvalue problems. And also you can see some information in the linear algebra its application by Gilbert Strawn. And there is another one book by Lee Kyan, Accuracy and Stability of Numerical Algorithms. So before going to your computer, you can see whether how much difficulty you have. Okay. So by looking your problem, whether how much accuracy will be coming. So this, if you know some numerical linear algebra technique, you can get all these things. Okay. So if you have any question, you need to.
Yes, we have time for.
Yeah, let's have a question discussion.
All single matrices are inconditional.
All?
Single matrices are inconditional.
Yes. All singular matrices are inconditional.
Also, we can also, or the non-linear. Then all non-square matrices are inconsistent.
All non-square matrix? All non-square matrix, it depends on this. Yeah, of course, it is a ill-conditioned matrix, but you can know the finding the singular value sigma 1 divided by sigma r. You just take from here. If it is very far from your this one, all non-square matrix you can find the singular values. Okay, but in general, non-square matrix is only this. Okay, and how much ill-conditioned it is. From here you can decide. Correct?
It means if the smallest singular value is
Yeah.
very small,
If it
the matrix will be
is
ill conditioned.
high.
In that way, we can predict ill conditioning,
Yeah.
compute singular values, and if last singular value,
Yeah. This.
several last singular values
Yeah.
are small, very small, then
Then
this matrix.
that's why this is the definition. Sigma 1 divided by sigma r is the rank of the matrix in the R. Even if it is non-square
Sigma
or
is very small.
Yeah. Yes, if it is far from 1, then you can say this is ill-conditioned. That's
So it is one way how to predict ill conditioning, compute singular values. Is it possible to predict ill conditioning according to structure of matrix or according to some another indicators?
Yes, if a matrix is a well conditioned, if it is unitary orthogonal, always well conditioned. Okay, this is always condition number 1. But how it, say for example, we have seen a Hilbert matrix. As you go and increase the size of the matrix, condition number is increasing. Okay. For your problem, how you need, what kind of condition number you need, and so that you can allow your solution to that make sense. It is up to you, it is individual's problem. So for example, for me, say for example, I make the switch of the bulb. If it is giving light after 5 minutes, for you it's okay. For me it is not. So I need immediate. Okay? Exactly. You make the switch of the bulb and it should get the light immediately. And it takes some time. Exactly. And sometimes it will take 2 minutes. For you, it's okay. So it comes in that. And for him, it is not. No, I should get immediately. The light should burn immediately. Okay. So how much error you are now? This is depends on your problem. Ill conditioning means it is far from one. It is deep. Not.
Any condition matrix can be made well conditioned.
Yes. You can, but it is hard. Can be hard. You know. It is difficult to solve. Even non-similar matrix also ill conditioned. Because defective matrix is ill conditioned. Yes, but it is not similar. Defective matrix, it is not similar. It is not like that non-similar. Say for example, Hilbert matrix. Symmetric, positive is definite. It is very. So this
Sorry,
yeah,
all is with best intention, but I found something provocative for research here. Page 119. 19 it was. And 2 or 3 pages later, here is K2.
this one?
Before this one, examples.
Yeah.
K2 of H4 is something power 4. 8 power 10.
10.
Then you have for H3, H6,
Yeah.
and later. Okay. Yes. H3 power 2. It looks provocative to investigate the relation between order of age and okay. It looks provocative to investigate relationship there is between order of H matrix of Hilbert matrix and power on right hand side, if it is not investigated so far.
People have investigated and carefully they are doing their research with the epsilon neighborhood, in the change of this epsilon neighborhood. If people are, for this kind of problems, people, say for example, my problem A is a matrix and it is simple thing. And say it is my Hilbert matrix, say. Hilbert matrix, or it is sometimes it is not Hilbert matrix, it is simple, and if eigenvalues are very, very close to each other, if they are very close. Even a simple matrix, you will get the wrong result. It is a yield condition matrix if this very, very close to each other, because condition number is equal to of eigenvalue. This is 1 divided by x star 1. And this is left and right eigenvectors. If the matrix is simple, this is not equal to 1. Left and right eigenvector. And if it is defective, and this would be equal to 1. So their condition number would be in. That my one. And in this case, what we are doing? We are changing this delta A naught in the epsilon level. In the epsilon, where A plus delta A, if it is defective, and you can make this matrix to simple. And in this case, the delta A and the change of this, either you can take 2 norm or you prognose norm or any norm you can take equal to 1 to infinity. We can make it, but this is the hard problem. Very hard problem. This is
We
NPR.
know structure of Hilbert matrix and probably using this structure.
Yes, again, the problem is structural. If it is Hilbert matrix, you have to check this delta H would be Hilbert. Again a hard problem. The structure preserving elements. If it is symmetric, then symmetric propagation, and you get this result. Sometimes.
I didn't understand what is in Hilbert space matrix. Is this perturbed Hilbert matrix?
Perturbed.
Still Hilbert.
Yeah. Perturbed Hilbert matrix. This one. This. People are, there are some works people are doing. In this case, you get paper after 5 years.
Such
And then-
provocative
And
problems.
you can get publication in sand and that's okay. If you work with it, and maybe 2 years you will get publication. It is not for 1 year, 100 pages. No.
Provocative problems from one side.
One problem is make this 5 years. Because this is the difficult.
Finally published.
Yeah.
It's one good journal is
Yeah.
better than published 5.
Exactly.
Not so good paper.
But one can try this kind of problem, even there are a lot of other things.
And another provocative problem for research.
Yeah.
You mentioned say
Like,
the time varying matrices.
Yes.
For me, it will be time varying.
yeah, it's rather
Matrix is dependent on parameter.
current.
It can be time, for example. In GMN, continuous time model.
Because there is a lot of application in dynamical system, bifurcation. I get really, it decides stability norms.
And my idea is to consider air conditioning,
No,
conditioning
Yeah, yeah,
in a
yes,
time varying
yes,
case.
yes, yes. Yeah,
Why not to consider
Yeah.
matrix A of T?
yes,
It depends on time.
of course, this is different from time.
And what will be with the neural network then?
Yeah, that we have to think, yes.
Also hard problem.
Yeah, no problem. But we keep continuing, maybe sometimes thinking it. But start
If
thinking
we
from.
have help from younger research, possible, it will be possible to solve faster.
Yeah,
Finally, it is good because after first result, research will not stop. Research can
yeah,
continue.
because a lot of connected works we have, we can continue. Because, see, many problems are solved. Easy problems, if you are thinking to work, sometimes you putting you in danger zone. Yes, because everybody has done. So what to do? So you have to take your problem, challenging problem, whatever you are doing, that will be the result. Understood me? You are taking the hard problem, whatever information you are getting, that is yours. Not. Yeah, any other question?
Finally, in the continuous time neural network, we can consider noise.
No, yeah.
Additive noise, for example, is similar as this perturbation.
Yeah, perturbation, because here you see, when the differential equation you are taking and the convergence analysis, if the matrix is diagonalizable, then good with that. If it is not, then you can go either Jordan canonical form or triangularization, or you will be going by what it is the hard problem, getting this convergence and all this things. So you have to go towards generalized concepts.
But it is possible to consider another kind of noise.
Yeah. Yes, yes, noise, yeah, all this.
It can be reflected on different kinds of air conditioning.
Yes, exactly. See, in mathematics, what they are doing, suppose that we see. They are doing it for the convex well condition. And you have a lot of things to solve. Take it for convex. Once it is non-convex, make it to convex. Then sensitivity analysis is playing in small thing. And you just come to the domain. And you apply your primary theorem, what you are doing in this case. This is completely a saddle control. Saddle control.
Okay, it is question for younger researchers here. So we can
Any
continue
other-
after our course.
Yeah, okay, thank you so much. We'll stop here. We have a final debate.
I sent you you spoke the.
Yes.
I sent you.
But the, yeah, but after,
Okay. Video. Okay, we can start. Welcome to our first tutorial. We decided to implement this tutorial interactively. I will work directly from my computer and MATLAB on my notebook. We spoke in morning about GNN model, gradient neural network model, and presented two gradient neural networks models. We spoke about two steps necessary to develop GNN model. First step assumes to define appropriate error matrix denoted by E of t. Only applicable rule for E of t is that zero of error matrix should be solution of our problem. Typically, we obtain E of t replacing unknown matrix in considered problem by time varying matrix V of t. In first case, we wanted to find matrix inverse and consider matrix equation and x equals I. Accordingly, we obtain error matrix equal to 8 V of t minus I. After that, we used the Frobenius norm to define goal function. Goal function is square of Frobenius norm. Instead, second step of GNN model, we used the kind of gradient descent method, gradient descent optimization method to minimize error function. We spoke when we minimize error function, we need to minimize norm. Minimum of matrix norm must be 0. And only zero matrix has 0 norm. And if we minimize Frobenius norm, we will obtain, we will force E of t to 0. If we force E of t to 0, we will solve matrix equation A V of t equals I identity matrix. And in that way, V of t will be approximation of matrix inverse. Here in 3 is a GNN model which we developed. This model is aimed to approximation of matrix inverse. Because we will use this model frequently, I write here this GNN model in table to be always available for you. Then we developed a more general model aimed to solving linear matrix equation AXB equals D. Error function is defined simply replacing X by by time varying matrix B of D. Goal function is square of Frobenius norm of such defined error function. And then we apply GNN dynamics, which relates time derivative of V of T with the gradient, negative gradient of goal function. In case of matrix equation, we will obtain such GNN model, such GNN dynamics, GNN evolution. We can use different techniques. It is one kind of dynamical system. Dynamical systems typically assume differential equations. Here in both considered GNN models, we have system of differential equation. Each element in left and right hand side matrices which represent one differential equation. So solving our dynamical systems assume solving system of ordinary differential equations. Technical problems. So we need to solve system of ordinary differential equations. MATLAB has a standard function for solving ordinary differential equations. This function is so-called ODE, ordinary differential equation solver. And several different ODE solvers are included in MATLAB. Our goal in this tutorial is to implement such two GNN models and try with some numerical experiments, try with different values of parameters, for example, different values of parameter gamma, try with different time intervals, try with the different blocks included in MATLAB. Here was part of presentation about nonlinear activation. We presented three standard classical, first nonlinear activation functions, such as linear, bipolar, sigmoid, power sigmoid, and in 4 and 5 we presented two activation functions which initiate finite time convergence of model. We spoke that each activation function must be based on odd and monotonically increasing function. Here is nonlinear model, which includes some nonlinear activation function. We want to make implementation in MATLAB and prepare some numerical experience. So this tutorial will be aimed to development of Simulinks for such two models. What is Simulink? First question is, Simulink is efficient tool for software development. Simulink is a graphical representation of system created within the Simulink environment, which is part of MATLAB. It enables users to design, simulate, and test systems using a block diagram approach, where different components are represented as blocks connected by signals. In general, Simulink is made of blocks which are connected by signals. Users can create models by dragging and dropping blocks from libraries, representing functions, components, and systems. It means that in a MATLAB environment, we will have one library of different blocks with different functions, and we will be able to include wanted blocks simply by dragging and dropping in our Simulink model. Why Simulink is used? Simulink is used to model, simulate, and analyze dynamical systems. Why use Simulink instead of MATLAB? It is possible to write MATLAB program instead of prepare Simulink model. But Simulink models provide visual representation of our system, which can help you to verify its logic and behavior. On the other hand, MATLAB code requires you to write and edit text commands, which can be more complex and error-prone. In any case, Simulink model is useful to trace design of our problem. Behind this Simulink model is corresponding MATLAB program. We can write MATLAB program. For some problems, I have MATLAB programs, but it requires MATLAB programming and will not be so used. So we decided here to use MATLAB Simulink for implementation. There is a list of frequently used blocks from MATLAB, which we will use in our implementation. If I list and these names and function, probably it will be tedious for you. We will see Simulink model and explain their function of different blocks. Here is a picture which represents the main blocks which will be used. It is a block where we can put constant value. Double click will open this block and you can put the corresponding constant value. Here is a block for product, absolute value, plus. We can define number of pluses, number of minuses. Gain is here. We will use this block to define our gain parameter, gamma. Display will represent the result. We will use this block to see current value of approximation, current value of matrix V of t here in our case, because V of t is approximation of matrix inverse or solution of matrix equation. Scope is aimed to graphical representation of obtained result. During time, scope will trace behavior of functions which we want to trace and prepare in graphical illustration. Sim out is useful because all results go to workspace, and after finishing simulating model, we can use these results and prepare the picture, analyze in different ways statistically or as we want. Block for matrix multiplication. Here we can define number of inputs. We can use properties for this block, and there will be possible to define inputs. Output is only one. Trigonometric functions. Very important integrator. It is part of this model. Integrator is aimed to solve these systems of matrix equations. Here we can choose all the solver which we use to solve this problem. Mathematical function. We can use this to compute transpose, matrix transpose. Subsystem. If we want to put another, say, subsystem, another system, subsystem inside this block, we can do this. It is kind of subprogram. And here is interpreted MATLAB function. Here we can make MATLAB program. We can put here MATLAB functions. Name of this block is interpreted MATLAB function. We will have this block in our application. It is list of main blocks which we will use in our implementation. Then it will be necessary to make connection to define signal between two blocks. Connect output from one block to input to another block and define stream of evolution in GNN model. Here is a model for computing matrix inverse. we will analyze this model. I will open you this model in MATLAB. Visible? Can be better. We can, we will go from beginning. Input is matrix A. And another input is identity matrix. I defined by standard function I. Double click on block A. We can see here only A, which means in command line we must define matrix A. Similarly, we will not work until we not define matrix A. There is possibility to define the matrix A here directly. We can define A here directly, but I choose here to define A in command line. Finally, for me, it is better, I think. Here is definition of identity matrix. I must write this definition. I is defined as I. It is standard function for identity matrix, matrix with ones on main diagonal, all dimensions, size of A. So when we define A, I will be defined immediately after that. It is our input. And then we will trace stream from input to output. We need to prepare right-hand side of our GNN model. Right-hand side of our GNN model. And we will do this part by part. First, we will define AV product. V is output of ODE solver. In initial time moment, V of t will be V0. So we need to define V0. Here we define V0 is here. We need to define what will be here, what will be in this stream in initial time moment. Later, we will obtain its iteration. We will obtain result using this result of this part of simulating. This part of simulating will give result in all another time moments. In initial time moment, we should define here what will be. Here is V0, which means our decision will be how to define V0. Theoretically, V0 can be arbitrary, and we will try with different V0 values, initial values. Here is AVT. Next, we need to prepare to define expression AVT minus I. We go step by step, expression by expression, from multiplier, plus, minus, and prepare right hand side. Visible now, plus, minus. Here is plus, there minus. Okay. Here is equivalent form, log of P equals gamma A transpose I minus A B of P. Okay, it is the same. Gamma I minus or minus gamma A B of T minus C. So minus is corresponding to string A B of T. Plus is corresponding to string which goes from identity matrix. Here is plus corresponding. There is minus. So result will be I minus A V of T. Here I put one textual comment about the result. I minus A V of T. This result must be multiplied by A transpose. This result must be multiplied by A transpose. Here is A transpose. A prime. In MATLAB, A prime is equal to A transpose. A prime is standard function for A transpose in MATLAB. And we can directly multiply I minus A V transpose by A transpose. Upper string is first in multiplication because matrix multiplication is not commutative. So if we want A transpose in beginning, string for A prime, string from A prime must be above, and down is string for I minus A V of T. And there is down is possibility to choose nonlinear activation function. Nonlinear model is defined as gamma A transpose nonlinear activation in this Simulink two nonlinear activations are included: power sigmoid and smooth power sigmoid. Functions mentioned by 2 and 3 in our list of nonlinear activations. Double click here is inside this block is MATLAB function called power sig. And here is implementation. It is element-wise application of function called PS. Here is definition of function PS. It is function which we use we showed previously. Now it is not so easy to change screen. Input is number 3, which means exponents. X, which means I minus v of t, here and here. And another value parameter rho. Here is a switch where we can change stream. Double click on this switch will change our choice. If this connection is in upper position, we will use linear. If we use double click, we will change direction of connection. I will use double click now. And now we stream goes down and we will go to nonlinear activations. And there is another switch, and double click here can change choice of nonlinear activation. Upper position will use power sigmoid activation function. Down position will choose smooth power sigmoid activation. For beginning, we can use linear activation. It means upper position here. Final result will be right hand side of this one. F, calligraphic F means nonlinear activation and can be linear when we have no practical activation. Double click will enable power sigmoid or smooth power sigmoid activation. And this right hand side goes to ODE solver, main part of Simulink implementation. It is most demanding part for this internationalization. We believe in ODE solver available in MATLAB. Name of this block is integrator. Double click. Here we can find V0. Here is V0, which means initial state. V0 must be defined from command line. V0 is used in time t equals 0 when we had no computations on right hand side before. It is in the beginning of our simulating modeling. Here, if we put here, it is single light settings. It seems relative visibility is relatively good. Click on this symbol and you can choose here solver. First, you can choose here solver. There is a list of several solvers, only 45, 15S, 23, and so on. OD 15S is my favorable choice. Stiff, possibly. It is OD solver for stiff problems. Theory says that ODE 55 is best. Probably the theory knows better. The experience of many people know better. My experience is that OD 15S is much faster. Typically, I choose OD E15S. If you have problems with implementation, if you have problem with slow modeling, slow running during time, you can, the good choice is to, good decision is to make another choice, to try with a different solver. Probably another solver can be more appropriate for this problem, for the problem which you want to solve. Here is number of parameters. Here you can define tolerance, relative tolerance. Again, if you have problems with implementation, it is good decision to change, to try with smaller tolerance. It is possible that smaller tolerance will give solution of your problem. Fixed step or variable step solver, variable step solver is better. It proves then MATLAB will decide about step size in solving successive systems of differential equations. After integrator, output of integrator, of our integrator, is V of t. By output of our integrator is V of t. We assume that ODE solver solved different system of differential equations. V of t equals something. Then output is V of t. But it will be V of t in new time instant. We choose a relative step size, and according to this choice, MATLAB will decide how step size for new time instant. And in this way, we can go back in our model. If we go back to our model, then again, we will make matrix multiplication to define AVT. Then again, I minus a v of t, but with new value of v of t. Value of v of t in new time instance. And again, because of such cycles in streams, GNN is kind of recurrent neural network. Because of such modeling in time, GNN model is continuous time model. Simulink is appropriate for dynamical systems defined in form of systems of differential equations. Okay, I will change. To be visible all. Okay, we can zoom. Here is specified end of our time interval. We must specify a time interval in which we will trace our simulink. There is 10 power minus 1. So we will consider here time interval 0 to 10 power minus 1. Short time intervals are preferable. You should obtain convergence in short time intervals. Long time intervals are not desirable. I use typically long time intervals when function which we'll consider is trigonometric and then tries behavior during time. Here is display block where we can see current value of v of t, current value of output. Here is time scope model, which will give trajectories of v of t. And there is another time scope models which will give value of Frobenius norm. Here is interpreted Natal function norm of used Frobenius. Here is common norm, standard Natal function u from. We spoke several times that matrix norm is not unique. There are several matrix norms available. We want here Frobenius matrix norm, and this string from means that MATLAB will use Frobenius norm. Time in MATLAB simulink is not denoted by t, it is denoted by u. U is standard notation for time used in a simulink model. So Here is norminf workspace, which will store values of Frobenius norm of error function. Here will be stored values of Frobenius norm of error function, and later we can plot stored values of Frobenius norm of error function. It's time to define input and try A must be defined. We have one example here in our presentation. Here is this example. Or we can prepare new using rand integer, rand I command. How can I share map? I want to use I want to take this three. Visible, okay. I equals around I. Not command. Random integers. We want random integer matrix with entries from this interval, 3 times 3 matrix. And after this, we can expect that matrix will be invertible. Almost is impossible randomly generate from time interval 110 and obtain singular matrix. I must type again, I suppose, using text from PDF. I use here some meaning is changed, some signs are changed. And when I retyped this, I obtained the randomly generated matrix. Also, we need to define V0. For beginning, we will use 0 initial state. Back to command line. Zero, say only 0. This, it should work. V0 equals 0. MATLAB will understand that there will be zero matrix. But I think I had some situations when MATLAB didn't understand this. We will solve this problem. And here is one important detail which must be explained. Here is gain parameter gamma Gamma is already defined here, 10 power 5. We spoke that gamma should be as large as possible. According to time interval 10 power minus 1, it is expectable that value of gain parameter equal to 10 power 5 should be enough. If not, we will see. Probably time to start. Finished. What does it mean? You cannot see here. Here is yellow line. Plot the yellow line to 0. Almost from beginning. I will increase beginning. Huh? Can you see difference? Here is. It means very fast convergence. It was convergence in after 0.03. We can choose shorter time interval. If we use double click on this time scope, we will obtain graphs of approximations. Here are the graphs really. Graphs, different graphs. Visible, blue is visible. Here is one graph. It means straight convergence, fast convergence from beginning, stable convergence. Use plus. Must use plus many times to see difference. Here is. Now we can see that convergence starts fast from one high gradient, and then quickly goes to stable stage. Here is another, because we obtain this matrix, and we obtain here all elements of matrix, trajectories of all elements of matrix. Plus, plus, plus. Here is difference. Now we can see trajectory of this element of matrix V of t. V of t is matrix, and here we obtain graphs of all elements. V3 goes to stable stage. Conclusion is that time interval is too long. According to selected gain parameter gamma. We can shorten time interval. Try with shorter time interval, 10 power minus 4, for example, 10 power minus 4. We had time interval 0 to 10 power minus 1. Now we make experiment with 0 to 10 power minus 4, shorter time interval. What will be in this case? Let's see something. What is conclusion? With convergence to stable equilibrium state, I found appropriate. This stable state is called equilibrium state. Each element of approximation matrix V of t goes to equilibrium state. Not so quickly, better to say, quickly in the same way as in previous time. But time interval is shorter, and we can see behavior of each element of approximation V of t during time. What happened with the matrix norm? Here is matrix norm. In any case, goes quickly to zero. Quickly to zero is our goal. It was our original intention. Force error matrix to zero. Zero of error matrix will be solution of our problem. Now we will reduce time interval future to see what will be. For example, 0 to 10 power minus 9. It is a very short time interval. Here we have small time interval. Gamma is not so big, only 10 power 5. But it depends on problem. Some problems require bigger gamma, longer interval. This problem is stable according to suffix speaking. Well conditioned. This problem is well conditioned. Hilbert matrix we can put here and see what will happen. I didn't try so far with Hilbert matrix.
Yeah, we should.
We can try. What will be then? Must use full speed. Sometimes after previous running, MATLAB uses only power, and you say, oh, find convergence. But I use full speed, and we can see here that time interval is too short. Is still not obtain convergence to zero. I cannot see here values on values here. You can see in my laptop, I will say you 1.718. Approximately here is 1.7, 1.8, better to say. What happened with V of t? Here is graph of element-wise graph of V of t. During my presentations, I typically say this graph, the reply com, because the graphs are as pale in morning after sleeping, the reply com. This com is increase of time interval. We need to increase time interval slightly, 10⁻⁸. What will be then? If I go back to our time intervals previous, of course, I will take the same result. To find appropriate time interval convergence, but with minimal length of time intervals. Still requires comp. Not so vertical, slightly more horizontal, but still not enough convergence. Value here is around 1.6. Bigger time interval. -6, we tried, so it's not so far. Next time interval is 0 to 10⁻⁻6. End of this trajectory looks as first attempt to find the equilibrium state. For example, this one goes, better to place this one, almost goes to equilibrium state. Longer 10⁻⁻6 is not enough. What happened with the error norm? Error norm is better and better. Value here is approximately 0.7. There is approximately 0.7. Point 0.5. Oops. 0.4, 10⁻⁻4 looks better. It is beginning of stable situation. It is beginning of stable situation. Here is value of V of t in last time moment. In time instance, 10⁻⁻5. 10⁻⁻5. What was result B which we can expect? I must go to presentation to see what is the result. Okay, we will analyze this later. Now I will make another experiment I will put here smaller value gamma, 10 power minus 3. Results are not so good as in previous case. Yeah, convergence is not achieved. Stable situation, equilibrium point is not achieved. Conclusion, this gamma is not enough for this time interval. If we choose longer time interval, 10 power minus 1, result will be better, right? Again. Actually. Smaller gamma, longer time interval. It means smaller gamma, slower convergence. Ten power minus 2 will be enough also. Ten power minus 4, it was enough for gamma equal 10 power 5. Not enough. If gain parameter is 10 power 5, then time interval 0, 10 power minus 4 is enough. It requires gamma equals 10 power 5. In this time interval, it is enough to use 10 power minus 10 power 3. What will be if we request convergence in extremely short time interval, 10 power minus 10? It is really very short time interval. 0 to 10 power minus 10. What will be with our gamma equal to 1000, 10 power 3? Really not enough. Only beginning. Far from equilibrium points. Is really far from equilibrium points. But if we use gamma equal to double click, 10 power 9, possible. Still not enough. For such short time interval, 0, 10 power minus 10, even gamma equal to 10 power 9 is not enough. We get 10 power 12 as large as possible. It's enough. Confidence. Stable equilibrium points.
You ask doubts if they have some interval, doubts,
Some interval.
any clarification if they have. Yes?
Okay. Okay, they ask,
If you have trimmed out, you will be trimmed out. Whether you are going through all this or not.
and understand something.
Because it's presenting, if you won't get, then get with even with. And ask your doubts. Do you want more, you will say, clear reaching into the.
I expect it to be more clear, much more clear after this tutorial, but my impression is that now the situation is not so clear.
Sure. So any doubts? No? If not, we will continue.
Bigger gamma, then we go to borders of MATLAB possibilities, 10 power 15. We obtained where is norm. But if I reduce future, I future reduce time interval, again we will be in the same situation. And another possibility is 10 power 16, and it will be increasing gain parameter. Right. 14. $18 here. Not enough. Bigger value, and so on and so on. If we want to obtain predefined time convergence in a strongly precise interval, then we must use nonlinear activation. Because we cannot obtain predefined time convergence using bigger values of gamma. We can try with some bigger value here, but MATLAB has limitations. No, still no. I think this border of MATLAB possibilities. Double precision arithmetic. Okay. Better choice is to include nonlinear activation. We will try now. Put here gamma equals 10 power 3 and time interval 10 power minus 5. Because I expected, according to previous experience, that this model will not complete convergence. What happened with norm? Not convergence to 0. Started fine. It is fine beginning. Now our idea is to we work with nonlinear activation already. Here is the linear case. And you see here, double click. Here is linear case, here is nonlinear. Here is power sigmoid and smooth power sigmoid. What linear case will say? What will be with the nonlinear activation, for example, power sigmoid? Now we can exploit this workspace. It will be good to compare behavior between nonlinear activations. Slightly longer time interval. Nonlinear activation. We will use command line and print results stored in norm_inf. First, start linear model without activation. You can see it, we will start this choice. Norm_inf. Plot norm_inf. Normally, I had many open graphs. It is plotting of results stored in norm_inf. Now we can prepare the figure if you want to write paper or something. Best choice is to use option view property editor. And then we can change all details as we want. Select detail on the figure which we want to solve, and here is property editor down. Down is property editor where we can change properties of this graph. For example, what we can change. Select. Can change width, make width, change color, then marker, put markers. Can change font size of font in the x-axis. color. And put another color if you don't care. X, Y, Z axis. Log scale. Linear scale. More properties. To investigate. We can investigate all these properties when you install MATLAB. Each component of our figure can be changed in many different ways. After that, when you prepare all as you want, font size should be increased. You can use command file save as typical, file save as, and then save your work typically as fig file. Here is fig as extension. If you save this figure as in fig extension, you can use later this fig file and modify future. You prepare the paper, prepare the figure in paper, but later you are not satisfied. Reviewers have some comments, then you can use fig file and again modify your figure. Another choice is to use apps extension. Apps. If you use apps extension, you can import your figure in LaTeX. But later, if you want to change, you must use fig file. Or again, start simulating, modeling, and prepare new apps file, new fig file. So it is good to prepare a fig file for all your figures. So you can change later simply without MATLAB implementation. I will close all figures. And again, I will call plot command. Plot norm in. Then I will use another gamma, for example, this moment. Then put here command hold on. Don't forget hold on. If I don't put hold on, then your figure will be over old. Plot norm in. Hold on. Change gamma. Here was previously was gamma equal to 10 power 3, and then again we will ask for norm in. Okay. Hold on. Okay. Gamma should be 10 power 5. Okay. Start. What will happen after plot norm in again? Difference is visible. Upper graph is for gamma equals to 10 power 3. Lower graph is derived using gamma equals 10 power 5. We can use bigger gamma. Don't forget, hold on. Otherwise, you must start from beginning. Hold on. 10 power 7. Start. Then again, plot. Yellow, you can see here, yellow line. And be bigger. I will use plus. Here is faster and faster convergence. Hold on. Gamma equals 10 power 1. Okay, 10. Plot. Command line. Here is. And see upper graph. Almost we have no convergence. 10, 10 power 3, 10 power 5, 10 power 7 visible that bigger values of gamma imply faster convergence. If you put here 10 power 5, for example, I think here is result. 10 dots to 8 e minus 13. 10 minus 13 is value of last value of norm. Result achieved almost 0, 10 power minus 13. Plot norm in. Hold on. Then nonlinear power sigmoid activation. Plot norm if in here is difference. Blue is linear model, and orange red is non-linearly activated model. There is difference, but not so strong as in case of increasing gamma. Typically, better, larger effect is obtained if we change gamma drastically, then use activation function. Another activation function will give probably slightly different. Again, not hold on, don't forget. Choose smooth power sigmoid activation. Run model. Then plot norm inf. What happened? Visible. It is difference between power sigmoid and smooth power sigmoid. Red, orange was power sigmoid, and yellow is smooth power sigmoid. Smooth power sigmoid is best choice. File print preview, save as, again, save as file, and then you can modify future. View property editor, and then you can change your model. Change, here you can trace behavior, X and Y values. You can make the X file of this figure and import X file in LaTeX file. I will not make save changes. No. It's time to consider another model. We promised in the beginning we will investigate two models. We investigated on the model for matrix inversion. It's time to investigate the model for linear matrix equation. Open this model. Oh, I have problems to find Simulink models. After imaging after 1 year, how will be difficult for me to find this model, AXB. It is model for it's nice. Again, input is given in as matrices A, B, and D. We must define A, B, and D. Again, I will find better, more illustrative. Not ZNN, AXB, for ZNN, GNN, AXB. Situation is the same. Input ABD, here is product of what is first A, second term is V. How can I recognize that second term is V? Because it is output from integrator. Output from integrator is V of T. AV and then third stream B. Here is AVB. AVB. Next step, D with plus and AVB related with minus. Double click, here is list of signs, plus minus, plus minus. We can change it in the minus plus, in minus minus plus plus as we want. Here we need plus corresponding to D and minus corresponding to AVB. And after that, we will obtain residual D minus AVB. Here is residual A minus VB. Step by step, as in previous case. After that, we need we can use nonlinear activation. Here, we didn't use nonlinear activation. This switch is in, if this switch is in upper position, we will go directly use string from B minus AVB. If we make double click here, we will change string to this position and use nonlinear activation functions as in previous model. Here we can choose between power sigmoid and smooth power sigmoid choice. Output is F, nonlinear activation of residual matrix, error matrix D minus AVB. It is our residual matrix. Here is a function which defines multiplication by A transpose from left and B transpose from right. Of course, we can use Simulink blocks for A transpose and B transpose and do this in classical way. It is for homework for you. Next tutorial, you can prepare a Simulink implementation which will not use this MATLAB function, part of MATLAB programming. Here we can put A transpose, B transpose, and then make new multiplication. We can try it here. Type. Here is after that integrator. 1 by S is simple for integrator. Integrator is aimed to solve this system of differential equations. Output of integrator is V of t. In the left hand side is V dot of t. After integration, we can expect V of t. Initial condition here is set to 0, opposite to previous case when we had V0, which means we need to define V0 in initial state later. Here, initial condition 0 is stated. Here is a two workspace block which will collect values of V of t. Later we can plot V of t. Here is a workspace block for residual Frobenius norm. And here is time scope block which will plot the results. We can try one example. Here is example in our, how to say, material, and we will try with this example, which is available in material. To spend your time, I used all what I use definitions of matrices A, B, and D in textual file. I prepared in morning for this presentation in textual file. Otherwise, it will take some time to type this. It is input corresponding to this example in our guide material. I will use copy. Now I should have no problems because this file is textual file. Previous I used from PDF file, I did not obtain possibility to work immediately. A, B, and D are defined. If I use semicolon after this comments, then result will not be displayed. What we need to define more? Initial state is 0 is defined. Gain parameter is defined. Function for Frobenius norm. Norm U from Frobenius. I think it's time to try. Okay, stable convergence. Here is a graph of state trajectories of matrix V of t. Stable convergence. And then one long-lasting equilibrium stage. Here is the convergence to zero. And then goes theoretically in infinity time to zero, to exact zero, but you can find an approximation in short time. Short time is 10 power minus 1, I think. Here is not 10 power minus 1. Sorry, because here is power 10 times 10 power, I cannot see here, and 10 power minus 9, which means in 10 power 10 we have minus 10. We have conversions. Then we can reduce value of gamma, 10 power 4. Conclusion is that 10 power 4 is not enough for such short time interval. Bigger values of gamma are desirable. Or if we increase time interval, we will obtain the same result. Again, one solution to obtain better results is to increase gain parameter. Another solution is to increase time interval. Now I want to consider theoretical result about convergence in time which we have. It is, I think, around 25 minutes. Over already. But we didn't start in time. We started in 4 p.m. I think.
10-minute delay will start.
What?
10 minutes.
Okay, we will only trace behavior according to initial state. Theorem 1. Says that this condition should be satisfied for consistency, and final result is defined in this way according to initial state. Our initial state is V0 equal to 0. V equals A dagger B. Is it possible that we can slide?
Sharing is short.
Only to see behavior according to the initial state matrix. I like this is theoretical result. Initial state defines final result. Finally, it is expectable. Do you remember our motivation for nonlinear optimization? We start from mountain and want to find minimum. If we start from another, we should try here with I need there's a few references. I apply what will be there. I will try to prepare for meeting.
Which PPT?
I think not up. Here it is. It is can be increased. Okay, it is. Thank you. This result which we obtained, zero initial state, so we can expect result A dagger B, B dagger. Minimum norm least square solution. Best approximate solution. What will MATLAB say? Professor Saul told that MATLAB includes standard function PINF, can I say PINF? P-I-N-D of A. Star is for matrix multiplication. D star PINF of B. And we can compare this result from command line with the result here. Here we can use format, double click, format short, format long, and obtain with more decimal digits. Can compare and see Okay. Looks, 3 decimal digits. How can we obtain 4 decimal digits? Can, if we increase gamma. How can I shade this? I want to change this and shade map up. Previous situation was fantastic. I could change easily. Increase gamma and power 6. Okay. Secret can be increased. Okay. Okay. Works. Interpretation. I read. It is the result for arbitrary gamma. Run with bigger gamma. Compare common line. Yes, now we have coincidence with at least 4 decimal digits. We can try with another initial state, for example, A transpose, A3. appropriate initial state should be in accordance with dimensions here, right here. A was of dimensions five times three. P is of dimensions four times three. So V of P should be 3 times 4. Appropriate dimensions. Now we obtain completely different result. Observe this result and previous result visible here. We can find V0 equals identity 3, 4. And then try to compute result A dagger pin star D star pin of B plus V0 minus pin of A star B0 star B star pin of B. Observe similarity. Now 3.2719 in any case. Approximate this result is similar as this above. Different V0 change result completely. What will be if increase time interval? Result should be more and more similar if we increase time interval or increase gamma. Results are more and more similar. So I hope you were able to see something about Simulink implementation. I only want to mention, it is necessary to mention that library browser is here. Here we can choose blocks which we want to involve, and we commonly used blocks are our blocks. And we spoke about drag and drop and include in improving simulating. Then make connection of this block. There's this line, can you see? Connect with another, and successful. Okay. Or may copy paste from the same simulink. I don't know why we can not make collection. Interactive work is from one side good, from one side difficult for professor. It should be connected. Now, if we disconnect A, what will be? I cannot make new connection. I suppose that MATLAB does not work. Editing not work here. If you have some questions.
Questions? Questions, please.
I expected a lot of questions after the tutorial.
That's a they were listening very carefully. Yes.
Is sometimes easier after this tutorial or easier? Because in the lecture we scroll the show it is simulating model, it is result. Now we can verify increase gamma, obtain better convergence.
This hit and run. You are putting various touches of gamma.
Gamma.
Yeah.
And increase gamma, decrease gamma, increase time interval, change in the initial state.
Appropriate one you are choosing, the for which.
Yes, tried to find appropriate.
So while using the power sigmoid activation function for finding the Moore Penrose inverse, if we take a substantially large gamma, we naturally expect it to
Reduce gamma.
reduce the convergence. But what happens is that it due to complexity and large gamma, it also had the numerical issues. And so how to counteract with the balance between the nonlinear activation function and the max possible gamma.
If we choose non-linear activation, we will reduce need to use such big gamma. We can use smaller gamma if we use nonlinear activation, because we watched situation when two nonlinear activation increased convergence. But typically, bigger gamma is faster way to increase convergence than nonlinear activation. Such two nonlinear activations considered here. We have better nonlinear activations. But nonlinear activation, more computations, more flops, because we will have powers and so on for each element of matrix. Simplest model is linear model.
And
And while solving the differential equation with the system, the method which we were solving it, we can choose any of it and it will converge. But how much of the error contributes it by the method we choose? So is it substantial error by the method we will choose, or the error is negligible? It kind of is it irrespective of the method we choose, or it heavily depends on the method we choose?
Depends on the
The method by which we solve the differential equation. So, the RK55 and all that.
method which we use to solve system of differential equations. Depends. If we change ODE solver, we will obtain different results. Sometimes, my experience is that ODE 45 is very slow, and then ODE 15S is better, it's faster. So we can we can change parameters. You think about parameters in ODE solver. These parameters. Of course, changing this. Here is also. Here is possibility to change solver. If we change solver, we can expect different results.
Yeah.
Numerical errors are unavoidable. Always.
So
In each time moment, solve different system of differential equations. In next time moment, solve. We cannot expect exact results.
So now which server is best?
Which
Server is best one? ODE solver.
solver? My favorite solver is ODE 15S. In literature, favorite solver is ODE 45.
ODE.
ODE 15S is for SIP solvers. In any case, I think it is fastest.
Yeah.
Fast.
One has to see again. If you change the solver, then you run out.
Change solver, change parameters in the solver, change gamma, change time interval, change initial state. Most safe initial state is zero initial state. If you have no convergence for non-zero initial state, try with zero. Possibility they will take.
Is there any technique to get this gamma easily as that is? Because you have a lot of choices here. Different gamma demand.
Not possible to predict in advance.
Okay.
Depends on or ill or well conditioned problem. It depends. If you change matrices, probably we will obtain different.
So one is to see the conditioning of matrix from there. One can decide, okay, this much gamma would be like this. Is there any like that?
It
Is
will
there
be
any
interesting to
connection
investigate
with the
conditioning here.
There must be. Means ill conditioning and well conditioning. The gamma will be changing.
We spoke about this
Yeah.
possibility to
So
consider
we'll check what the
conditioning
the ill
time varying case. In case with one parameter, parameter here is time.
And then. Okay, any other questions?
Is there any,
Yeah.
is there any limit for gamma?
I expected limit to be in 10 power 17. But for 10 power 20, you can get something.
Thank you for the also for gamma.
You limit for gamma, a limit of MATLAB.
For gamma.
Gamma.
Here we consider 10
10 parameter gamma. In one moment we choose 10 power 20. and obtain better result than 10 power 17.
The gamma is not fixed, there is no, but we can try with very, for 10 to the power 5 for this convergence square. Easy. Is there any other questions? If no, let's give big thanks for.
Not saving. We can stop sharing. And I will shut down my computer. Typically after such corrections, the resolution is changed. Shutdown is best choice.